let's start by looking at all the geometry and the labeling in this problem. Here I've redrawn the picture, but I've used some different letters because I think their letters in their picture are confusing. This force up here, they've labeled F sub W in their picture, but I think W is a better name for it. It's the wall force, and it's straight horizontal. Down here, they showed both a diagonal force from the floor and the two components. I only want to show the two components, and I'm going to name them differently. This horizontal component of the force from the floor on the ladder is friction, so I'm going to call it friction. The vertical component is the normal force, so I'm going to call it the normal force. And it says that this distance here is 3 and that distance up there is 4 meters, I think. That's what meters. Now we're going to have to deal with both of the angles in this big triangle. So this angle down here, I'm going to call this angle X, and I'm going to call this angle Y. Now, if we have a triangle that is 3 over here and 4 over here, then this side has to be 5. That's a 3, 4, 5 triangle. If this is X and this is Y, right, when we do our torques, we're interested in the sine of X and the sine of Y, right? Well, the sine of X is going to be side opposite over a hypotenuse. That's 4 over 5. The sine of Y is opposite over hypotenuse for Y. That's 3 over 5. Okay? So we know these sines. We don't have to go and do something fancy. We know what they are. Now, let's look at the angles between our forces here. This angle right in there, that is angle Y. See that? It matches with that angle. This is also angle Y in here. And this guy up here is alternate interior with that. You see that? So this angle up here is X. So now we're ready to do just about anything. So the first thing I always do is forces. So I look at this as if it's a spread out free body diagram. I'm going to make my X and Y equations. Well, these are really easy because all of my vectors are horizontal or vertical. In the horizontal direction, all I have is the friction force and the wall force. That's it. So all I've got is F minus W has to equal 0 because it's not moving. That's really easy, and in fact that tells me that the friction force is equal to the wall force. In the Y direction, we have normal force going up and these two weights going down, mg minus big mg. That has to equal 0, so that tells me that the normal force is equal to the total weight. What this problem is asking for is the coefficient of friction, which is, of course, the friction divided by the normal force. All right? So we've got the normal force here. We just need a better expression for the friction because we don't know what this wall force is. So we need to do something else. And that's why we need to do torques. So I am going to use as my center of rotation this point down here, because by choosing that point I can eliminate 2 torques from my torque calculation. And it doesn't scare me that I've just eliminated the friction because I know the friction is equal to the wall force and the wall force is still here. So that's what I'm going to do. So my first torque is going to come from little mg. So here's its lever arm. Its lever arm I call 0.5 times the length. So the first torque there is, remember, torque equals RF sine theta. So my first torque is 0.5 times the length, that's the lever arm, times the force, mg, times the sine of y. But the sine of y we've determined is 3/5. So that's my first one. Second one is going to be from big mg. That's the person standing on the ladder. So I draw my lever arm. This one is 0.7 times the length because they said 70%, right? So this one's going to be 0.7L big mg and also sine of y. And these two torques are both going to tend to pull the ladder downward or clockwise, so I'm going to make them both positive. So this is 0.7 L big mg times 3/5, because that's the sine of y. And then my last torque, I have this whole distance, which is L, the length of the ladder. So that's L. And I have the force is W, but now my angle is X. So this is going to be sine of X. And this one is pulling the opposite direction from the other two torques, so I'm going to make it negative. So I have minus LW, instead of sine X, I'm going to put 4/5. And that has to be equal to 0. So I can divide each of these terms by L, because they all have an L in there. Get rid of that. And so now I see that my W is going to be equal to 0.5 times little m times g times 3/5. Oh wait, this is a mistake. This should be plus, right? Plus 0.7 times big mg times 3/5 over 4/5. So that way I can calculate W, the wall force, which is equal to the friction, see? And now I could put that in here, I could put this in there and calculate the coefficient.